Before the Airbus A350 ever touched the sky, before its carbon fiber body reflected sunlight at cruising altitude, and before airlines praised it as one of the most advanced wide-body aircraft in history, Airbus was facing an existential threat. This aircraft was not born from ambition alone. It was born from pressure, competition, and the very real possibility of losing dominance in long-haul aviation forever. In the early 2000s, Boeing had changed the rules of the game. The Boeing 787 Dreamliner promised lighter weight, lower fuel burn, longer range, and unprecedented passenger comfort. It was built around one radical idea. Composite materials would replace traditional aluminum. Airlines listened. Orders flooded in. Airbus, for the first time in decades, found itself reacting instead of leading.
Airbus initially believed it could respond with a simpler solution. Instead of building an entirely new aircraft, it proposed an upgraded version of the A330, a design that had already proven reliable. This aircraft was called the A350 in name only. It shared too much with older designs and too little with the future. Airlines were unimpressed. Major customers rejected it outright. The message was clear: this was not enough. What followed was one of the most critical decisions in Airbus history. Airbus scrapped the original concept entirely and started again from zero. What emerged was not an upgrade, not a compromise, but a clean-sheet aircraft. It would be wider than the 787, longer-ranged, structurally different, digitally designed, built for decades, not years. This new aircraft would redefine Airbus engineering philosophy. They called it the A350 XWB, extra wide body.
From the beginning, the A350 was designed with one core principle: efficiency without sacrifice. Airlines wanted lower operating costs, but passengers wanted comfort. Pilots wanted advanced automation, but engineers wanted safety margins. Regulators wanted compliance, but Airbus wanted innovation. Balancing all of this required a level of precision aviation had rarely seen before. More than 50% of the A350's structure would be made from carbon fiber reinforced polymer. This material is lighter than aluminum, stronger under stress, and resistant to fatigue and corrosion. But composites behave differently than metal. They do not bend the same way. They do not crack visibly. They require new inspection methods, new repair techniques, and new manufacturing standards.
Airbus was not just building an airplane, it was building a new industrial ecosystem.
Factories were redesigned. Robots replaced manual processes. Entire sections of the aircraft, barrel segments of the fuselage, were manufactured as single pieces. Wiring, traditionally installed late in production, was digitally mapped and integrated early. Every component was modeled virtually before being built physically. This reduced error, but it also meant there was no room for improvisation. If the digital model was wrong, the aircraft would be wrong. One of the A350's most revolutionary elements was its wing. Long, slender, and aerodynamically optimized, it was designed to flex dramatically during flight. At cruise, the wings bend upward by several meters. This is not a flaw, it is intentional. Flex reduces stress and increases efficiency.
But designing a wing that flexible, while ensuring it never fails, required extreme precision.
Airbus engineers tested the wings beyond breaking point, literally. During certification testing, the A350's wing was bent upward until it snapped. The braking load exceeded expectations. The test confirmed what Airbus needed to prove. The aircraft could withstand forces far beyond anything encountered in service. This was not about passing a test. It was about earning trust. Inside the cockpit, the A350 represented a new generation of Airbus philosophy. While maintaining commonality with earlier Airbus aircraft, it introduced advanced avionics, larger displays, improved situational awareness, and refined fly-by-wire logic.
Pilots transitioning from the A330 or A340 could adapt quickly, but the aircraft offered deeper layers of automation and protection. Every system was designed to assume one thing: humans are skilled, but humans are not perfect. The flight control laws were refined to provide smoother handling, better energy management, and stronger envelope protection. The aircraft actively assists pilots in maintaining safe flight parameters, but without removing authority. This balance between automation and control was one of the A350's defining characteristics. For passengers, the changes were just as profound. The carbon fiber fuselage allowed higher cabin pressure and increased humidity. This meant less fatigue, fewer headaches, and improved comfort on long flights. Windows were larger, the cabin was quieter, air quality was cleaner. These were not marketing features, they were physiological improvements. Airbus understood that modern aviation was not just about getting people from point A to point B. It was about how they felt when they arrived. But none of this came easily. The A350 program faced delays, cost overruns, and intense scrutiny. Supply chains struggled to keep up. Composite manufacturing proved complex. Early production aircraft required rework. Schedules slipped. Critics questioned whether Airbus had taken on too much. Internally, pressure was immense. The A350 was no longer just a product, it was a statement. Failure was not an option. The first flight took place in June 2013. As the aircraft lifted off, years of engineering, billions of euros, and the future of Airbus traveled with it. The flight was smooth. The systems behaved as expected. The aircraft performed within parameters. It was not a celebration, it was a relief. Certification followed extensive testing. Cold weather, hot weather, high altitude, maximum weight, emergency scenarios. Every system was pushed. Regulators examined data in microscopic detail. The A350 passed. When the aircraft entered commercial service, airlines quickly noticed the difference. Fuel burn was lower than expected. Range exceeded promises. Maintenance costs were reduced. Dispatch reliability climbed. Passenger feedback was overwhelmingly positive. The A350 was not just competitive, it was dominant. But the real story of the A350 is not just about technology or efficiency. It is about survival. Airbus did not build this aircraft to innovate for innovation's sake. It built it because the future demanded it, because the industry was changing, because standing still meant falling behind. Every rivet, every composite layer, every line of code in the A350 carries the weight of that moment in aviation history, when Airbus chose reinvention over retreat. This aircraft is the result of pressure, precision, and purpose. And in the next part, the story goes deeper, into the design battles, the hidden risks, and the moments where the A350 nearly became something very different. When Airbus committed to building the A350 XWB, it was not just designing an aircraft, it was entering a design war. A war against time, against physics, and against a competitor that had already reshaped expectations. Boeing's 787 Dreamliner was no longer a concept, it was a reality. Airlines had seen it, touched it, ordered it. Airbus now had to do something far more difficult than innovation. It had to outperform. The pressure was immense. Every design decision carried consequences measured not in kilograms or dollars, but in market survival. The A350 could not simply match the 787. It had to go further. Longer range, wider cabin, better economics, greater flexibility. Airbus engineers were given a clear mandate: no compromises. One of the earliest and most controversial decisions was fuselage width. Airbus chose to make the A350 wider than the 787.
This allowed more comfortable seating configurations, wider aisles, and larger galleys. For passengers, it meant a noticeable difference. For airlines, it meant higher payload flexibility. But for engineers, it meant increased structural challenges and weight penalties that had to be eliminated elsewhere. Every extra centimeter mattered. To offset this, Airbus doubled down on advanced composites. Carbon fiber would not just be a feature, it would be the backbone of the aircraft. The fuselage panels, wings, and major structural components were designed using layered composite architecture, optimized digitally down to individual fibers. This was not traditional aircraft manufacturing. This was aerospace engineering at its most unforgiving. Unlike aluminum, composites do not show fatigue in predictable ways. Cracks do not propagate visibly. Damage can be internal. That meant Airbus had to rethink inspection, maintenance, and long-term durability from the ground up. Airlines demanded answers. Regulators demanded proof. Airbus responded with data. Massive amounts of data. Test panels were stressed, struck, frozen, heated, soaked, and pressurized repeatedly. Engineers simulated decades of service life before the aircraft ever flew. They analyzed how composite layers behaved under lightning strikes, bird impacts, runway debris, and emergency landings. Nothing was assumed. Everything was measured. The message was clear. This aircraft would not enter service until every unknown had been confronted. Another battleground was aerodynamics. The A350's wing was designed using advanced computational fluid dynamics, far beyond what previous aircraft generations had used. Every curve, every angle, every surface transition was optimized to reduce drag and improve lift efficiency. The result was a wing that looks elegant, but behaves aggressively. At cruise altitude, the A350's wings flex upward dramatically. This flex is not a sign of weakness, it is a sign of efficiency. Flex reduces structural loads and improves fuel burn, but designing a wing that can bend so much without failing required engineers to push materials to their limits. They tested until those limits were exceeded. During structural testing, the A350 wing was loaded incrementally until it reached more than 150% of its maximum design load. Only then did it fail. The wing bent like a bow before finally snapping. The test validated not just strength, but predictability. The wing failed exactly where engineers expected it to fail. In aerospace, predictability is safety. Inside the cockpit, a different design war was taking place. Airbus had built its reputation on fly-by-wire technology and cockpit commonality. Pilots loved it, airlines loved it. But critics argued that automation could distance pilots from the aircraft. The A350 had to strike a delicate balance, more automation without less awareness. The result was a cockpit that looks familiar to Airbus pilots, yet behaves more intelligently. Displays are larger and more customizable. Systems are integrated more deeply. Alerts are prioritized to reduce overload. The aircraft does not simply warn, it explains. Flight control laws were refined to handle the A350's size and performance. Energy management became smoother. Protections were strengthened. But Airbus intentionally preserved pilot authority. The aircraft assists, but it does not dominate. This philosophy was deliberate. Airbus engineers studied past accidents, human factors research, and pilot feedback extensively. They understood that safety is not just about preventing mistakes. It is about making the right action the easiest one to take. This was a lesson learned over decades. Another critical decision involved engines. Airbus selected the Rolls-Royce Trent XWB as the exclusive power plant for the A350. This engine was not adapted from an older design. It was built specifically for this aircraft. More efficient, quieter, more powerful. but also incredibly complex. The engine had to deliver exceptional fuel efficiency while meeting strict noise and emission regulations. It had to perform reliably on ultra-long-haul routes, and it had to integrate seamlessly with the A350's digital systems. Engine and airframe were no longer separate entities. They were a single ecosystem. As development progressed, the scale of the challenge became clear. Supply chains struggled to keep up with composite manufacturing demands. Some components arrived late, others required redesign. Assembly lines slowed, schedules slipped. Critics began to question whether Airbus had taken on too much. Internally, the pressure intensified. Engineers worked relentlessly. Delays cost billions. Every missed milestone was magnified by the shadow of competition. Boeing was watching. Airlines were watching. The world was watching. But Airbus did not retreat. Instead, it refined, adjusted, reinforced. Problems were solved methodically. Systems were revalidated. Manufacturing processes improved. The aircraft matured, not quickly, but correctly. This patience would later become one of the A350's greatest strengths. By the time the aircraft approached its first flight, it was no longer just a response to the 787. It was something else entirely. Bigger, quieter, more capable, built with lessons learned from every success and failure that came before it. The A350 was no longer chasing the future. It was shaping it. And in the next part, the story moves from design tables to the sky, where real-world testing would reveal whether this aircraft truly lived up to its promise. Long before passengers ever stepped inside the Airbus A350, before airlines painted their logos on its fuselage, and before pilots trusted it with their lives, the aircraft was pushed to the edge of destruction on the ground. In aviation, belief is never enough. An aircraft must prove itself repeatedly, brutally, and without exception. For the A350, this proving process was unlike anything Airbus had attempted before. Testing did not begin with engines or flight. It began with assumptions. Every assumption engineers had made during design had to be challenged. Could composite fuselage panels withstand decades of pressurization cycles? Could the wings endure extreme turbulence year after year? Could the digital systems respond correctly to failures that might never occur, but still had to be anticipated? Airbus built full-scale test articles that would never fly passengers. These aircraft existed for one purpose only: to be abused. They were bent, shaken, frozen, overheated, overpressurized, and pushed far beyond what any operational aircraft would ever experience. One of the most critical tests involved repeated pressurization cycles. Each time a commercial aircraft climbs to cruising altitude, its cabin is pressurized. When it descends, that pressure is released. Over decades of service, this cycle happens tens of thousands of times. In metal aircraft, this process slowly creates fatigue cracks. In composites, the behavior is different and less forgiving if misunderstood. To address this, Airbus subjected A350 fuselage sections to accelerated aging tests. Pressure was applied and released again and again, simulating multiple lifetimes of operation in a fraction of the time. Sensors tracked microscopic changes in the structure. Engineers watched closely for delamination, internal fractures, or unexpected deformation. The results confirmed the design. The composite fuselage not only met expectations, it exceeded them. But structure was only part of the story. Systems testing was where the A350 truly distinguished itself. The aircraft was designed around an integrated digital architecture, where avionics, flight controls, engines, and monitoring systems communicated continuously. This created efficiency, but also complexity.
A failure in one system could not be allowed to cascade into others. Engineers simulated failures that pilots might never encounter in their entire careers. Electrical failures, sensor disagreements, data bus interruptions, engine anomalies, hydraulic losses. Each scenario was introduced deliberately to see how the aircraft reacted. The goal was not to prevent failure, that is impossible. The goal was to control it. In every test, Airbus watched for one thing above all else: predictability. The A350's fly-by-wire system was designed to interpret pilot inputs intelligently, even during abnormal situations. Control laws adjusted automatically. Protections remained active. But crucially, the aircraft never removed pilot authority entirely. This was a conscious design choice rooted in decades of operational lessons. Flight test pilots were deeply involved in this process. Their feedback shaped refinements to handling characteristics, alert logic, and automation behavior. If a system surprised a pilot, it was redesigned. If an alert created confusion, it was simplified. Surprise is the enemy of safety. Environmental testing was equally unforgiving. The A350 was exposed to extreme cold, simulating operations in polar regions. Systems were tested at temperatures far below freezing. Materials were evaluated for brittleness. Electronics were monitored for reliability. Then the process was reversed. The aircraft was tested in extreme heat, representing desert operations and tropical climates. Air conditioning systems, avionics cooling, and engine performance were all pushed to their limits. The aircraft had to function reliably, whether operating from frozen runways or scorching tarmacs. Then came the wing tests, the most visually dramatic and symbolically important phase of certification. Engineers loaded the A350's wings with enormous force, gradually increasing stress beyond operational limits. The wings bent upward dramatically, far more than passengers would ever see in flight. Cameras recorded every millimeter of movement. Sensors measured strain across the structure. The wings did not fail when expected. They continued bending, absorbing energy, behaving exactly as predicted by the models. Only after exceeding 150% of the maximum design load did the structure finally break. This was not a failure. This was success. It proved that the aircraft could survive forces far beyond anything it would ever encounter in service. Flight testing followed ground testing, and it was exhaustive. Multiple test aircraft flew thousands of hours across continents. Every flight profile was explored. Short flights, long flights, high altitude, low altitude, heavy weight, light weight. Test pilots deliberately placed the aircraft in uncomfortable conditions, not to scare themselves, but to expose weaknesses. They practiced rejected takeoffs, engine failures after liftoff, rapid descents, abnormal configurations, and emergency scenarios. Each maneuver was evaluated not just for safety, but for workload. How much effort did it take for a pilot to manage the situation? Were controls intuitive? Were alerts clear? An aircraft can be technically safe and still be operationally dangerous if it overwhelms the crew. Throughout this process, regulators observed closely. Certification authorities demanded evidence for every claim Airbus made. Every test generated massive amounts of data. Every data point was reviewed, questioned, and verified. The A350 was not approved because it was impressive. It was approved because it was understood. By the time certification was granted, the aircraft was no longer theoretical. Its behavior under stress was known. Its limits were defined. Its failures were mapped. Only then was it allowed to carry passengers. The testing phase revealed something important, not just about the A350, but about Airbus itself. The company had moved beyond traditional manufacturing into a new era of digital, predictive engineering. Problems were no longer discovered after entry into service. They were anticipated years in advance.
This approach would define the A350's operational reputation. In the next part, that reputation would be tested where it truly mattered, not in laboratories or test ranges, but in real airline operations, real routes, and real-world economics. Certification is not the end of an aircraft's story. It is only the beginning. Once the Airbus A350 entered commercial service, the true test began, not in controlled environments, but in the unpredictable reality of daily airline operations. Weather, schedules, maintenance pressures, human behavior, and economics would now judge whether this aircraft truly lived up to its promise.
The first airlines to operate the A350 approached it with cautious optimism. Expectations were high, but so were memories of other aircraft that had struggled in early service. Airlines are unforgiving environments. An aircraft must perform reliably every single day. Delays cost money. Cancellations damage reputations. Unexpected maintenance erodes trust. The A350 had no room for excuses. From the earliest months of operation, data began to emerge. Fuel burn numbers were closely monitored. Dispatch reliability was tracked obsessively. Maintenance reports were analyzed for patterns. What airlines found surprised even Airbus. The aircraft was outperforming its own forecasts. Fuel efficiency exceeded targets. Airlines reported significant reductions in operating costs compared to older wide-body fleets. On long-haul routes, the A350 demonstrated consistent performance, even at high weights and extreme ranges. This mattered deeply. Routes that were previously marginal became profitable. New city pairs became viable. But performance alone does not define success. Reliability does. The A350 quickly developed a reputation for exceptional dispatch reliability. Aircraft were leaving on time. Systems behaved predictably. Fault messages were rare, and when they did appear, they were often diagnostic rather than disruptive. This was a direct result of the aircraft's integrated monitoring systems, which allowed maintenance teams to address issues before they became problems. Predictive maintenance became a reality, not a promise. For airlines, this changed everything. Pilots, too, began to voice their opinions. Transition training was smooth. The cockpit felt familiar, yet refined. Automation reduced workload without creating detachment. The aircraft handled smoothly in turbulence. Energy management during descent and approach was praised. Many pilots described the A350 as intuitive, an aircraft that seemed to anticipate what they needed. This feedback mattered. In aviation, pilot trust is earned, not marketed. Cabin crews and passengers noticed changes as well. The quieter cabin reduced fatigue. Higher humidity and lower cabin altitude improved comfort on ultra-long flights. Passengers arrived feeling less exhausted. For airlines competing in premium markets, this became a powerful advantage. The A350 was not just efficient, it was humane. Yet no aircraft enters service without challenges. As the fleet grew, minor issues emerged. Software updates were required. Certain components showed wear patterns earlier than expected. Supply chains had to adjust to composite repair demands. What mattered was how these issues were handled. Airbus responded quickly. Updates were deployed. Procedures were refined. Operators were supported directly. Unlike past generations, problems were addressed collaboratively, with data shared across the global fleet. This transparency strengthened trust. The aircraft matured rapidly. Within a few years, the A350 was no longer considered new. It was considered dependable. The real-world success of the A350 forced comparisons. Against older Airbus models, the difference was dramatic. Against the Boeing 787, the competition became more nuanced. Each aircraft had strengths, but the A350's larger size, longer range variants, and passenger comfort carved out a distinct role. Airlines use the A350 on flagship routes, ultra-long-haul missions where reliability and efficiency mattered most. Some flights exceeded 17 hours. The aircraft performed consistently. This endurance revealed something important. The A350 was not just designed for the present, it was built for future operational demands that had not yet fully emerged. As global aviation evolved, fuel prices fluctuated, environmental regulations tightened, and public scrutiny increased. The A350's efficiency suddenly became more than a financial benefit. It became a strategic advantage. Lower emissions per seat, reduced noise footprint, improved sustainability metrics. These were no longer optional features. They were necessities. Airbus had anticipated this shift. By the time the aviation industry faced unprecedented disruption, the A350 stood as one of the most resilient wide-body platforms in service. Airlines that operated it found themselves better positioned to adapt, redeploy, and recover. The aircraft had proven itself, not through headlines, but through consistency. What began as a response to competition had become a benchmark. And yet, the story of the A350 does not end with success alone. In the final part, we examine the aircraft's long-term legacy, what it represents for the future of aviation, and why its true impact may only now be becoming clear. When the Airbus A350 became a regular sight in skies around the world, its story quietly shifted from innovation to legacy. The aircraft was no longer judged by specifications, test results, or early service reports. It was judged by something far more demanding: time. And over time, the A350 proved that it was not just a response to a competitor, but a turning point in how wide-body aircraft would be designed, operated, and trusted. The A350 arrived at a moment when aviation was redefining itself. Fuel efficiency was no longer just an economic concern. It was a political, environmental, and public issue. Noise, emissions, sustainability, and long-term viability had become central to aircraft design. In this environment, the A350 did not need to be reinvented. It was already prepared. Its composite structure reduced weight and corrosion. Its engines delivered efficiency without sacrificing power. Its systems architecture supported predictive maintenance and long-term reliability. These were not short-term advantages, they were foundations. Airbus had not built the A350 for a single decade. It had built it for a generation. As the fleet matured, airlines began using the A350 in roles that previous aircraft could not fulfill as effectively. Ultra-long-haul flights became routine. Thin routes became viable. Fleet flexibility increased. The aircraft adapted easily to changing demand, something the aviation industry would soon need more than ever. Pilots described the A350 as stable, predictable, and forgiving. Maintenance teams praised its diagnostic transparency. Passengers recognized it by comfort rather than by name. These quiet indicators mattered more than marketing claims. Trust had been earned. The A350 also influenced Airbus's future designs. Lessons learned from its digital modeling, composite manufacturing, and systems integration flowed directly into newer programs. The aircraft became a reference point, a standard against which future wide-body designs would be measured. Even competitors took notice. In aviation history, truly successful aircraft reshape expectations beyond their own manufacturers. The A350 did exactly that. It reinforced the idea that efficiency and comfort are not opposing goals, that automation can enhance safety without removing human authority, that advanced materials, when understood deeply, can outperform tradition without compromising trust. But perhaps the A350's greatest legacy lies in what it avoided. It avoided rushed entry into service. It avoided unresolved design compromises.
It avoided the burden of fundamental rework after deployment. These absences are not accidents. They are the result of restraint, discipline, and a willingness to delay rather than deliver something unfinished. In an industry often pressured by competition and deadlines, the A350 stands as proof that patience can be a competitive advantage. As aviation looks toward the future, toward sustainable fuels, new propulsion concepts, and evolving global travel patterns, the A350 remains relevant. It is efficient enough to meet modern demands and adaptable enough to integrate future technologies. It is not a relic of a past design era. It is a bridge. The real story behind the A350 is not just how it was built, but why it was built the way it was. Airbus chose reinvention over iteration, precision over speed, long-term resilience over short-term victory. That choice reshaped the company, the market, and the expectations of passengers worldwide. Years from now, when newer aircraft take center stage, the A350 will still be flying, quietly, efficiently, reliably. Not as a symbol of competition, but as evidence of what happens when engineering is driven by purpose rather than urgency. The A350 was not designed to win a race. It was designed to endure.